Welcome back. This is Physics 104B. We're looking at section 23, the electric field. Remember from chapter 8 when we studied gravitation, there is something called the gravitational field, and I'm going to relate the electric field to this. When you first learned about g, the vector lowercase g, you learned it as acceleration due to gravity. You learned it as 9.80 meters per second squared. But as we continued our studies in first semester, we learned that g is not just an acceleration measured in meters per second squared, but rather it is the strength of gravity measured in force per unit mass. So it refers to, for a given mass, how much force that mass would feel. And we can measure it in newtons per kilogram. And we found that dimensionally, meters per second squared is the same as newtons per kilogram. So when we thought about the electric field, when we thought about the gravitational field, we thought of it as a vector going down, like my picture on the left. But actually, if we zoom out on the planet Earth, it's not that the field points down, but rather it's vectors that point in towards the center of the Earth. And some things we learned about these vector field lines is that the closer they are together, the stronger the gravitational field. So you can see near the surface of the Earth, these field lines are tighter together, and that's where gravity is stronger. And as they spread out, they're not as tightly together, and that's where gravity is weaker. Well, mathematically, this is very similar to the electric field. We can see down at the bottom the law of universal gravitation that we learned in the first semester, that the force of gravity is the universal constant, the gravitational constant g, times the product of the masses divided by distance squared. Well, now we have the Coulomb law, the force of either attraction or repulsion, which is a universal constant that's related to the permittivity constant, times the product of the charges divided by distance squared. So just as there is great similarity mathematically between these forces, there's also great similarity between these fields. Here is the main equation for electric field as it relates to forces. The electric field at any point is the force per unit charge that a charge would experience at that point. So we have the electric field is equal to the force vector divided by that charge. So when we think about the concept of fields, I think about how Isaac Newton, when describing gravitation, he considered it an action at a distance. And he thought that it was absurd that two things could act on each other without touching each other. But as we think about fields, we can think of it no longer as an action at a distance, but rather responses to these fields that are everywhere. So a point charge has an electric field around it, and then another charge comes into the vicinity, and that charge responds to that field. Much like a mass, such as the planet Earth, has a field around it, and another mass that comes in just responds to that field. So the force on a charge due to the field is given by this equation, the force vector is that charge times the electric field. Now let's think about which way do the vectors point. The answer is the direction that a positive test charge would be forced. So if you think about on the left is a picture of a point charge with its electric field emanating from it. These electric field vectors, they point in the direction that a positive charge, if placed in the vicinity, would be forced. So if we put a positive charge right where my pointer is, then it will be repelled from the central point and it'll be forced upward. Now, what if we put a positive charge right here where my pointer is? Well, it'll be repelled away and it'll be forced in this direction. So those vectors point in the direction always radially away from that positive charge. Now we come over here on the right, to these oppositely charged parallel plates. We have a positive charge built up on the top plate and a negative charge on the bottom plate, and they cause an electric field, a parallel uniform electric field in the middle. Well, if we were to put a positive charge right here in the middle, we think which way would it be forced? It would be repelled by the positive up top and attracted by the negative down below, and so it would be forced down. So again, those electric field vectors, they point in whatever direction a positive charge would go if it were put in the area. And by the way, you can see in my box down below, if we were to put a negative charge in, then the force on that negative charge would be opposite. So we go to the picture on the left, and I have the electric field lines drawn, and you think, what if I put a negative charge right here on the upper left hand? Well, you know it would be attracted to the positive point charge, and so it would go opposite the electric field line. It would be pulled in. And what about my picture on the right? If we were to put a negative charge right here in the middle, it would be repelled by the negative on the bottom, it would be attracted by the positive on the top, and so it would be forced upward. It would go against the electric field lines. Let's look at an example in the book. This is example 20.3, which is on page 338. It says a charged raindrop carrying 10 microcoulombs experiences an electric force of 0.30 newtons in the positive x direction. So here you've drawn it. I've drawn out the information. We have the force is 0.30 I hat newtons. The charge is 10 microcoulombs, and I've drawn that force vector to the right. What is the electric field at its location? Now, because it's a positively charged particle, it is forced in the direction of the electric field. So while I drew the force vector going to the right, we also know that's the direction of the electric field. But we can do the vector math to show that the electric field also goes to the right. And by the way, also the question asks, what would the force be on a negative 5 microcoulomb charge at the same point? Okay, let's answer part A. The electric field vector is the force divided by Q. So we have the force of 0.30 I hat newtons. Notice I've written out in vector form. Divided by the charge, 10 microcoulombs is 10 to the negative 5 coulombs. So we have 3 times 10 to the 4th I hat newtons per coulomb. That's the electric field, the magnitude and direction. Now, question B says, what if we replaced it with a charge that is negative 5 times 10 to the negative 6 coulombs? Well, then the force would be Q times E, which would be negative 5 times 10 to the negative 6 coulombs times, we know the electric field, we just found that in part A, 3 times 10 to the 4th I hat newtons per coulomb, and we get negative 0.15 I hat newtons. So the negative I hat means it'll go to the left. But we could already tell that from the diagram, because if the electric field points to the right, we know a negative charge would go to the left. I want to now talk about the field from a simple point charge. This is the simplest kind of electric field from a single point charge. We have the electric field is the force on what we'll call a test charge divided by that test charge. And we know what the force would be. So imagine the point particle that's causing the field. I'll give it a charge of capital Q. And then we imagine, as we try to think, what would the force on a hypothetical charge that gets brought into the area, let's call that hypothetical charge the test charge. So we know that the force between them is K big Q times test Q divided by R squared. But then in our electric field formula, we're dividing by the test charge. So it doesn't matter what the test charge is. And in fact, remember, the electric field, its presence has nothing to do with if a second hypothetical charge comes in. It's kind of like the gravitational field. We can talk about the gravitational force on a book from between planet Earth and a book, but the book doesn't have to be there for there to be an or a gravitational field. So just the same, the electric field that comes from our point charge with charge positive Q, it doesn't have to have any other charges present to act on them. This is just the field that emanates from our point charge. So what we get is the electric field from this point charge is K times Q over R squared. And remember, K is that 9.0 times 10 to the 9th times the charge divided by R squared. And it points in the R hat direction. Remember, R hat is the radial vector pointing away from our charge with a magnitude of 1. So if Q is positive, then this vector is going to point radially outwards. If Q is negative, it's going to point radially inwards. And you can see my pictures down below. With a positive charge, this is what the electric field looks like. The electric field lines point radially away. And if it's negative, they'll point radially inward. And by the way, it's really not radial. I say radial because this is a two-dimensional drawing here. Actually, it's spherical. It goes out in 3 dimensions. As we finish up this section, let's look at 2 problems, 2 very simple problems in the back of the book. They're simple because you only have the one equation coming out of this section. Number 22 says, find the magnitude of the electric force on a 2 microcoulomb charge in a 100 Newton per Coulomb electric field. So here I've written out the given information. Electric field is 100 newtons per coulomb, and the charge is 2 times 10 to the negative 6 coulombs. It's not asking about direction, so we don't need to treat this in vector fashion. We can just use the scalars. So the force is E times Q. 100 newtons per coulomb times the charge of 2 times 10 to the negative 6 coulombs, and we get 2 times 10 to the negative 4 coulombs is the force. Number 24 says the electric field inside a cell membrane is 8 meganewtons per coulomb. What is the force on a singly charged ion in this field? So here we have the electric field is 8 meganewtons per coulomb. That's 8 times 10 to the 6 newtons per coulomb. A singly charged ion. So this is an atom that has either an electron, an extra electron, or it's missing an electron. So the charge is either plus or minus E. We don't really know based on what the question says, but that's okay because we're really looking for the magnitude of the force. So we'll use the equation that force equals electric field times charge. I've used the absolute value sign because all we're caring about is the magnitude, not the direction. So the electric field is 8 times 10 to the 6 newtons per coulomb. The charge is 1.602 times 10 to the negative 19 coulombs, that elementary charge. And we get 1.28 times 10 to the negative 12 newtons, which is 1.28 piconewtons. And a piconewton, that's a very, very small charge on the human scale, but for a single ion, it's quite an effective force. That is the end of section 23. Have a great day.